It's really great to be with you all. Um, I appreciate you coming by. So I was telling Erkao a few minutes ago that I'm used to giving this talk to like low dimensional topologists or just topologists who don't do a lot of symplectic anything. I'm at Georgia Tech right now where we have lots of like knot theorists that just it's hard to make them care about symplectic things sometimes. So I have to spend the first like half of the talk convincing people that Weinstein domains are worth thinking about. So maybe you already believe that, but I will try to convince you again. So if you're annoyed with me for telling you what a Weinstein domain is, well, I will try to make up for it with some more technical details later on. So everything I say today is joint work with Joe Breen, who is at the University of Iowa. And I should also mention if you when you see figures in this slides, probably if they're good, then Joe made them. I should give him credit for those as well. So the plan, the roadmap today is I first want to tell you about just like how to think about Weinstein domains as the right sort of object for doing Morse theory in the symplectic category. That's going to be the key distinction between Liouville and Weinstein for us, is that these are both symplectic manifolds where we can think about dynamics, but the Weinstein case, that's the one where we can think about Morse theory. Then we'll talk about trying to distinguish between Weinstein and Liouville domains. And there's an obvious or natural topological obstruction. I shouldn't say obvious, but a relatively elementary one. And then we'll start talking. So these two sections are background, and then these later two sections are, what if we try to explicitly turn a Liouville domain into a Weinstein domain? So a lot of my spiel, my opening there doesn't make sense if you don't know what Liouville and Weinstein domains are yet. But I'll try to sort of work through here towards what the goal of the talk is, and then maybe this outline will make more sense. All right, so if we think back to Morse theory on smooth manifolds, it really is a geometric approach to doing things, even if you're on a smooth manifold with no implicit geometry. And what makes it so important for us and what the Morse lemma is all about is this correspondence between Morse functions on a smooth manifold and handle decompositions of the smooth manifold. So when you see a critical point of a Morse function, that tells you that some handle is being attached as you build up your manifold from sublevel sets. So you start with the empty set, you see an index 0 critical point, and this tells you that suddenly a 0 handle is born. And then you keep moving up your sublevel sets and you see an index 1 critical point. This tells you that a 1 handle has been attached. And now your sublevel set is this cylinder. You keep moving up and you see another index 1. So you attach another 1 handle. And then finally you see an index 2 critical point. And so you attach a 2 handle. And I failed to color the top portion in a way that matches the first two. But the point is, this descending manifold of your critical point, this is your attaching data. This is the core of your handle that you're attaching. So this should be this entire disk up here is a core. Okay, so this is the fundamental reason a topologist would care about a Morse function. And it's also very useful and important that we have some understanding of how homotopies of functions, changing the function that you're using corresponds to a change in the handle decomposition. This is what surf theory is that as you watch the Morse function change over time, you can see the handle decomposition change, and you just are going to have these isolated instances where you fail to be Morse. So in this first section, titled Morse theory for geometric objects, we want to ask, what's the analogous theory when you also have a geometry in addition to the smooth topology? Well, we're going to do this by thinking actually about vector fields most of the time instead of directly thinking about the functions. Because when you actually go to write down this correspondence, the first thing you do is pick a Riemannian metric on your manifold and take a gradient. What you really care about is the vector field, which is the gradient of your smooth Morse function instead of the function itself. And so these three pictures, I hope you agree with me that this is how you compute the index, but I have to have this slide for the topologists because I've been yelled at before about the difference between an index 0 critical point and an index 2 critical point. I know there are topologists who will tell me that this is an index 0 because everything's going in, and this is an index 2 because everything's going out. Well, it's important for us today, for some statements I need to make later, that index is how many directions are going into your critical point. And these orange shaded bits of the boundary that you see here, that's the attaching region of the corresponding handle. So the attaching region, when something passes through that, it's headed towards the critical point. Okay. So we're going to move to a geometric setting and look for these same types of vector fields, but then we'll be asking for some compatibility between the vector field and our geometry. One technical point, I said we're only going to study the vector field, but we do require that the vector field be gradient-like. So loosely that it is the gradient of a function. It's just that we're not normally going to deal directly with the function. We're just going to pay attention to vector fields. This is an important distinction in a sort of technical sense, if you really want to be careful, but maybe not hugely important right now. It's just that gradient-like is a strictly larger class than actually gradient. So I don't really want to define what gradient-like is, but you can loosely think of it as just a gradient, except maybe I'm allowed to scale my vector field in weird ways, and I'm allowed to break things like the curl-free test that you teach your multivariable calculus students. So we want to look for vector fields which behave nicely with respect to handle decompositions and with respect to a geometry. All right. So a key feature, in addition to this compatibility with handle decompositions, the key thing that makes a lot of the engine work is that if you flow along the gradient of a Morse function, you get a diffeomorphism from the smooth manifold to itself. This is crucial to being able to actually turn our picture of the handle decomposition into a legitimate handle decomposition where you understand the gluings and you understand how to smoothly extend your smooth structures over the new handles. So if we're in a setting where M carries some additional geometric structure, then we want that flow, the flow of your gradient or gradient-like vector field, to be an isomorphism in whatever category it is you're thinking about. So it will be a diffeomorphism, but you want it moreover to preserve your geometric structure. So if you wanted to create a Riemannian handle calculus, I don't think you do, but if you did, then you would look for vector fields on the Riemannian manifold, which are gradient-like and therefore compatible with a handle decomposition, and moreover, have the property that flowing along them gives you an isometry. I can go ahead and disappoint you and tell you that if you look for these on a closed Riemannian manifold, you're not going to find them. But this is the sort of thing you would look for if you wanted to create a Riemannian handle calculus. So that's what we're going to be doing today, is trying to think about symplectic manifolds, which admit a handle calculus. All right, so this is the differential geometry and symplectic topology seminar. So I don't suppose I need to remind many of you what the contact and symplectic structures are, but whether you know what they are or not, the important distinction between them for us today is that contact structures they allow us to make conformal changes to a chosen contact form, right? So a contact structure is really just a choice of a codimension 1 distribution or a hyperplane field on a smooth manifold that satisfies some property, while a symplectic structure is a particular 2 form. So we talk about contact forms and symplectic forms, but there's a very important difference that a symplectomorphism must preserve a symplectic form. while a contactomorphism, it doesn't have to exactly preserve the symplectic form. It only has to preserve its kernel. So it can scale this contact form however it sees fit. Therefore, if we want a handle calculus in either of these settings, we want some vector field so that flowing along it either induces a conformal change in the contact setting, so we're allowed to have this scaling by G, or induces no change at all in the symplectic setting. So maybe that's a good point to stop and say, are there any problems with the story we're telling so far? All right. Well, we're not going to address the contact story today because it's settled. In the 90s, I should say, not only did Giroux show we always have contact vector fields, but we have gradient-like contact vector fields. So Giroux showed that, yes, contact manifolds admit handle decompositions. And there's a big industry built around this called convex surface theory, and now convex hypersurface theory. So in the contact setting, we can always do this, and it's crucial that we're allowed to make these conformal changes to the one form. In the symplectic setting, on a closed symplectic manifold, just as was the case in the Riemannian world, we're not going to find a vector field of this type. It's simply impossible. And here's the reason. On a closed symplectic manifold, omega, this 2 form, is required to have its n-fold product be a volume form on the closed manifold. So if we ask for the flow along X to preserve the symplectic form, then actually this is a volume preserving symplectic flow. If you have, I'm sorry, just flow. If you have a volume preserving flow, then the divergence will be 0. So you're not allowed to have sources or sinks. And if you're not allowed to have sources or sinks, then you couldn't be gradient-like for a function on a compact manifold, because a function on a compact manifold is going to have mins and maxes. So this is just never going to work. In the contact case, hard work of Giroux shows we always admit these vector fields. In the symplectic case, we just never admit them on a closed manifold. All right, so the consequence, or not the consequence, the workaround that has been found is, instead of requiring that flow along that vector field not change your symplectic form at all, let's mimic the contact case somewhat and allow conformal changes to our symplectic form. So this will be our replacement condition, is that when we flow along X, instead of requiring omega to be unchanged, in fact, omega will be expanding exponentially. So this is still more specific than the contact case where you just allow any conformal change, but it is modeled on what you see in the cotangent bundle. So that was, if you're well familiar with this condition, then maybe that was a lot of words to say things you already know. But even if you already know it, I hope that I'm able to put you in the frame of mind that we're trying to do Morse theory. This is really all this comes down to, so that we can do handle calculus in the symplectic setting. So this gives us our 2 definitions. A Liouville domain is going to be a symplectic manifold, except instead of being a 2 form here, this is a 1 form. This is the symplectic potential. The derivative of it is our symplectic form. And then there is a unique vector field which has this property, so that contracting that vector field into the symplectic form gives us back our 1 form. The choice of symplectic potential determines a vector field, and we require that to be outwardly transverse to the boundary. So this is going to look very much like a cotangent bundle and the dynamics thereon. And this vector field that you get, just by definition, it will satisfy the property that it's exponentially expanding the symplectic vector field, sorry, symplectic form. The distinction between a Liouville domain and a Weinstein domain is that in a Weinstein domain, we further require that Liouville vector field x lambda to be gradient-like for some Morse function. So on any exact symplectic manifold, you automatically have a vector field which has the correct flow property, this expanding property. That's just free on an exact symplectic manifold. To be Weinstein, this free Liouville vector field must additionally be gradient-like. And that's a much more difficult thing to be, but it's what allows us to do handle calculus. This is another good place for me to ask for questions.
So I maybe should have asked a few slides ago, but why was like the Lie, maybe I'm going to use the wrong words too, Lie derivative, like Lx of omega equals omega. Why was that supposed to be illuminating? Granted, I don't know that much about this stuff. How is that like a Morse analog?
Oh, I apologize. So it's not a Morse analog. There are two things we have to capture here. Let's see. We want our vector fields to be gradient-like. That's the Morse analog, is that they
Okay.
look like the gradient of some vector field, and therefore you can get a handle decomposition. And
Okay.
then at the same time, to be like in the nice geometric world and give us geometric handle decompositions, we ask them to give us isomorphisms in whatever category.
Okay.
And that's what this condition is, which is then
All right.
replaced by this condition. So this is not a Morse
Okay.
condition. The gradient-like is the Morse condition. The
Okay.
flow is just the geometric compatibility that we're looking for.
Okay.
Does that clarify?
It's a little better. Thank you.
So no, I appreciate this, because the very important distinction between Liouville and Weinstein here is that Liouville, we do have geometric compatibility. On any exact symplectic manifold, you get a vector field which is geometrically compatible. To upgrade that to Weinstein, you need your vector field to be Morse compatible. And that's the delicate, difficult thing to achieve that we're going to work on today. Okay, so if you want to
Thank you
do
for that
Morse theory,
clarification.
oh yeah, thanks for the question. I do appreciate it. So what we want to do today is say, all right, we always get the Liouville vector field. How can we make it Morse? That's how what the remainder of today will be. Just a remark, it's not super important. I mean, it is super important, but I don't think it was on anyone's mind, is that in all cases, we are going to have manifolds with boundary. This is just something that's forced on us by the geometry. You can't have a closed exact symplectic manifold. And the actual computation is here. But the point is, if your boundary were empty, then you would get some contradiction when you unwind this. So we still can't do Morse theory for closed symplectic manifolds. Not only can we not do that today, there's just no theory exists for that. But for closed symplectic manifolds with boundary, we can often do Morse theory. Sorry, compact symplectic manifolds with boundary. Closed didn't make sense. So then the question we want to investigate is, if I start with any random Liouville domain, what are the odds I'll be able to turn it into a Weinstein domain? Or can you have dynamics from that vector field you start with that are so crazy, you just cannot make them Morse-like. You cannot make them gradient-like. You can't tame them. Okay. So first of all, there's one obstruction that is easy to state. I shouldn't, it's not obvious. You have to kind of unwind quite a few definitions to make it clear, but it's easy to state, which is that if you have a Weinstein domain and you go and work out this geometric condition, then it turns out the Morse function for which you are a gradient or gradient-like it cannot have critical points of index greater than 1/2 the dimension. So for instance, in dimension 4, you can build a Weinstein domain using 0 handles, 1 handles, and 2 handles, but you're not allowed to use 3 handles when building your Weinstein domain. For surfaces, this proposition doesn't really enforce anything. It just says, except the fact that you have to have boundary. But in higher dimensions, Weinstein domains, they have to have connected boundary, for instance, because if you wanted to have a disconnected boundary, you would have to attach a very high index handle. And we're only allowed low index handles when building Weinstein domains. So there's the corollary, which, whoops, I had already said out loud. In dimension at least 4, if you have a Weinstein domain, then the boundary must be connected. So if you're a complex geometer, that sounds morally right to you because symplectic manifolds are even dimensional. They're somehow kind of like complex manifolds. And if you have a complex manifold with pseudo-convex boundary, the boundary must be connected. And it's the same case for Weinstein domains. So there are certain cases where we can say there's no way this compact manifold could carry a Weinstein structure. And in fact, there are Liouville domains, which you can prove do not admit a Weinstein structure because they have disconnected boundary. So McDuff in the early 90s gave the first example of such a thing. This was, I mean, the description is there. It's a unicotangent bundle of some surface minus a neighborhood of the 0 section. But the particulars of that construction aren't so important today. The point is, she built a Liouville structure on a domain with disconnected boundary. Therefore, this thing just cannot be turned into a Weinstein structure by the topology. It's not possible to tame the dynamics and make them Morse. Lots of examples now exist of such things. So McDuff's example was in dimension 4. She gave a 4D version with disconnected boundary. I want to walk through now an explicit example given, Mitsumatsu and Geiges both separately gave these like infinite families of examples. And from theirs, you can recover this one from either of those two separate families. So this family is neat. It starts with, it's very, very dynamical in nature. So you can start with a 2x2 element of SL2Z, it's a matrix, which is an Osav, in that it has this contracting direction and then an expanding direction. So it's got both eigenvalues are real, and then one is less than one and one is greater than one. If you have such a thing, then, well, it's sort of something to unwind that you can find these like eigen one forms, kind of like finding eigenvectors, but they're one forms on a torus. And as a result, you get a contact form on the torus, and I'm sorry, on the torus cross an interval. So you can, it's not important that we check this right now, but this contact form does depend on this capital A that you chose. And then we'll see the dynamics reappear. You can define a map from this contact manifold to itself, which contracts in the interval direction that you've introduced, so that this lambda2 over lambda1 will be less than 1 by construction, and then also applies this Anasav map. And the point of requiring such a thing, where you have these eigenvalues less than 1, greater than 1, is that these eigenvectors will have irrational slope. And so this will not have, this has no eigenvalue 1 is the real point. So you're never going to have any fixed points of this map A. So if you start at any point here and you back up, you're going to keep backing up all the way until you end up on this red skeleton in the middle. So I guess I should explain my cartoon a bit. I didn't do a good job of that. In this cartoon, this horizontal direction is the tau coordinate. And then a single point on that would be a T2. So when you build this partial mapping torus, you kind of flow straight backwards. And then when you get back around to 0, you apply this map. And so your tau coordinate will get smaller, and then you apply the matrix A. And by applying the matrix A, when your tau gets smaller, you make sure that this thing has no periodic orbits. Everything in backward time will just flow until it hits this, or at least it will approach that. And this skeleton here is the mapping torus of A as a map from the torus to itself. And so as a result, we have a four-dimensional Liouville domain whose flow is given by this blue vector field, which has disconnected boundary in these two separate pieces. And so it's not Weinstein. And then, oh, whoops, I zoomed in at some point. In 2020, Huang extended this construction to work in all dimensions. So in all dimensions, we have these Liouville domains, which just cannot possibly be Weinstein. And the real moral of this example, and the main reason I would bring it up in addition to McDuff's example from the previous page, is that it's true that the disconnected boundary is what stops this from being Weinstein. But what we want to think of it as is having just really chaotic dynamics. The dynamics of the Liouville domain are very difficult to tame. And turning a Liouville domain into a Weinstein domain ultimately boils down to taming the dynamics, making them Morse and making them compatible with a handle decomposition. What about now? Are there more questions?
I guess, okay, why did we not want any of the periodic orbits? Is that just because we're dealing with a torus, or is that something deeper?
So I guess I should first say the periodic orbits would create big problems for Morseness, because if you have a periodic orbit, then you're not the gradient of something, simply because if you flowed along that and you came back to
Oh,
where you
you're
started,
looping back.
then you're
Okay.
looping. But for the Liouville dynamics, you're still not going to be able to have that periodic orbit. Yeah, so maybe let's say it's for Morse reasons right now that will prohibit it. If you did allow yourself to have the periodic orbits, then you would still not be able to make this thing Weinstein. And I won't make a claim right now, but whether or not it would be Liouville. Yeah, it's a good question. All right. So the question though is, so there are lots and lots of examples that have been constructed over the last 30 years of these Liouville but not Weinstein domains. These Liouville domains which could not possibly be Weinstein. But in every example I know of, and everyone I've talked to, the only way you can prove that the Liouville domain fails to carry a Weinstein structure is this index bound. You just show that, oh, if I wanted to build this, I would need a handle of high index, and I'm not allowed to have handles of high index in a Weinstein setting. So this begs the question, if I start with a Liouville domain, and I happen to know that I could build the smooth manifold, the underlying smooth manifold, using only index of small dimension, sorry, only handles of small index, then could I actually tame the dynamics? Could I find a Liouville homotopy so that I can make this thing Weinstein? I don't know the answer to this. A simplification, which we will address, is the question of whether all Liouville domains are stably Weinstein. So stabilization is a process that takes a Liouville domain and crosses it with the disk, and you have to add something to the symplectic potential to get a new Liouville domain. But the point is, if your dimension was 2n before, then your dimension is 2n plus 2 now. When you do this, the topology doesn't get any more complicated. So the notion of being high index is changing because your dimension is increasing, right? So that Mitsumatsu Geiges example from the previous page, it was a four-dimensional Liouville domain, which required a three handle to build. and therefore couldn't be Weinstein. But if you stabilize it, it's now a six-dimensional Liouville domain. So three handles, those are legal. Maybe that three handle could be made Weinstein if you stabilize. Another way to think of this, and the way I would like us to think of it as, is that stabilizing gives us this extra dimension and gives us more room to possibly tame our dynamics when you go up in dimension. Okay, so that's the fundamental question we want to answer in the remainder of the talk, or work towards answering in the remainder of the talk, is can we find a way to homotope to a Weinstein structure once we've stabilized to satisfy the index bound? And as we've discussed repeatedly, we're treating this very much as a dynamical problem. So we're going to try to directly manipulate the Liouville vector field of our domain. So here's our toy picture, our toy example. This is a Liouville structure on the cylinder. So it's S1 cross the identity, where the S1 factor is glue the top to the bottom there. And the flow you see is the Liouville flow of an actual Liouville structure on the cylinder. So it has the right geometric properties, but it's certainly not a gradient because you have this periodic orbit. So it's just not gradient-like. Turns out this one's going to be very easy to fix. It's very easy to make this one Weinstein. And I'll show you how. But the way we're going to make all of our manipulations is by applying these local Liouville homotopies so that we can interrupt the cyclic flow lines. That could mean periodic orbits like this, or broken periodic orbits where broken flow lines where you have something that travels from point A to point B and then from point B back to point A. That would also fail to be a gradient. The Mitsumatsu Geiges example fails to be a gradient because you have these wandering flow lines which just kind of flow backwards forever and never run into a critical point. We want to be able to interrupt that flow using these compactly supported homotopies. So I'd like to be able to just take a picture of a flow box right here, change the flow in this region, and then end up with something where I don't have that periodic orbit anymore. And so I am gradient-like. So I think this proposition is like a good summary point. It's a technical proposition in the paper, but I think right now it'll help us sort of regroup on what the strategy is. A Liouville domain you start with will be Weinstein if and only if, first of all, in backward time, you need every flow line to converge to a critical point. And if you picture a handle decomposition for a manifold with boundary, that happens. If you flow backwards, you're either like if you take that torus from the start of the talk and take off the cap and you flow backwards, some points are going to run into that top index one critical point. Some points are going to run into the saddle at the bottom, and then others will flow all the way down to the index zero. But everything has to flow backwards to some critical point. The flow lines can't have any loops, like we've talked about, because then it wouldn't be a gradient. And then finally, near the critical points, you need to look Morse. So when I say has a Morse-Lyapunov function, I really just mean you are gradient-like for a Morse function around the critical points. So we're not going to worry about this condition as much. That's sort of generic, but we want to talk about local operations which can ensure these two phenomena occur. So we want to interrupt these cyclic flow lines. Nice. So the way we're going to do this is actually it's quite pictorial. So I'm hoping we can just draw a bunch of pictures and not have to do too many computations. But if you take any smooth function on a Liouville domain, you can turn this into a Liouville homotopy by just adding to your original symplectic potential the differential of your function. So this gives you a way to, when talking to your collaborator about Liouville homotopies, just talk about them as graphs of functions. And you say, why don't we install a bump here? Where what a bump means is you want to write down like the indicator function of some region in W, something that looks like a bump if you were to graph it. But really what you're doing is you're changing the Liouville form and therefore changing the vector field. So we're going to be clever in our choice of this vector field to, I'm sorry, clever in our choice of this function to control the vector field on the Liouville domain. And I'll show you a picture of one of these in just a second to try to drive home what we're doing. Oh, I'm showing you one picture now. So this Liouville domain in 2 dimensions is just a box. And this is supposed to be like a box that you could just choose inside of any other 2-dimensional Liouville domain. And the Liouville flow is just going straight through. But if you were to choose some function on this 2-dimensional domain and run through this argument where you write down a Liouville homotopy, the resulting vector field would point in that direction. So you started with something that just pointed in the S direction. Now you have some T component, and so you have to just cleverly and carefully control the S and T derivatives of F. So it becomes this sort of crazy balancing act of how do we control the derivatives of F in these 2 directions to force our flow to be directed in certain directions. This is all quite vague and a little hard to follow when it's just the simples, but more cartoons are on the way. So here's our first manipulation. This is called a box fold. What you're supposed to see here is that in this plane is a Liouville vector field in dimension 2. So everything right now is just flowing along these straight lines in that direction. And this was just a plane, but what we're going to do is think about the indicator function for this rectangle in the plane. And so what you see right now, this box you see, is supposed to be just the indicator function of that square, or that rectangle. And in reality, we would have to do like a smooth approximation to get a smooth Liouville homotopy, but we can just look at this piecewise linear box to think about what's going on. And when you do this and you pick up and turn into a box, that rectangle, well, you can go back and you look at what's the t derivative there and what's the s derivative here and chase down what the resulting vector field is, and you're going to find that the vector field will climb up and over this box and just pass through the box in some cases. And in forward time, it's actually in all but one point, it's going to just pass through. But there's going to be this range of values here where if you were flowing backwards on the other side, and you ran into the box, you would then flow up the box and then across it and then down and back and up and across and down and back and up and across. And you would just spiral around to be trapped in backward time. So one of the criteria we had for turning a Liouville domain into a Weinstein domain is that we wanted in backward time everything to get trapped. You wanted to run into critical points in backward time instead of looping around forever and ever or wandering around forever and ever. And the box fold, by introducing this box, we're able to trap a lot of these flow lines in backward time because they're forced to spiral around the graph here. And then what you would actually see. So this is how we think about and talk about the manipulations, as we think of them in graphical terms so that we can just plot these nice things. But in reality, this was supposed to be a 2-dimensional Liouville domain where you make this installation. And when you do that and you do smooth approximations to this box, what you end up seeing is previously everything just flowed straight through, like I showed you on the previous slide. Now you're going to have this green trapping region where the items which in backward time previously flowed straight through will now flow around and run into a critical point. So by installing these box folds on our domain, we're able to trap flow lines that previously just went straight through. Okay, I just kind of blew through the previous page to get to the cartoon. After the cartoon, what questions are there?
So you just replace the rectangle with the box, the out, not the inside, just the surface, right? And what is the F in this case?
So here in this piecewise linear case, capital F would just be the indicator
Oh,
function
I see, I see.
for that rectangle. So it's not even continuous, much less smooth. What you see here, this additional notation, it has to do with a smoothing parameter. So we sort of like however close you need it to be, you can smoothly approximate that indicator function. And then when you do that, you end up with a vector field that looks like this. Everywhere else, the vector field is unchanged. It's still just flowing straight. But now we've introduced all this trapping so that these points will be trapped in backward time. Thanks.
I have a question about, maybe this doesn't really matter, but like what made you know to do like trapping from like in negative time instead of like saying, oh, let's have a criteria where if we go in forward time, then everything meets at a critical point, or is that just by choice?
So it's not by choice. This is a great question. It's really about it's something, something from a while back with like the definitions of all these things. So when we look at what a Liouville domain is, we have to have a vector field which pushes out of the boundary. So for most points on the domain, if I just start somewhere on the domain and then flow in forward time, I'm going to flow out of the boundary and I'm just going to leave the
Oh, okay.
domain.
I
But in
see.
backward time, I have to run into the critical point.
Okay. So it's based off of like, yeah, what you're structurally working with. Thank you so much.
Thanks. Yeah, so it's the fact that our index has to be at most half instead of at least half. If it were the other way around, then we would do everything in forward time. And I absolutely agree that that is confusing. Like too many conversations with my collaborator have been like 10 minutes of us just sort of like yelling at each other, and then the other one saying, "Oh wait, it's backward time. You were right." Yeah, yeah. Like backward and forward time is confusing. Okay, so an even more cartoonish version of what we just did is this picture here. So we're returning these straight lines into this sort of trapping. And then the point is, if you were to install that here, you could actually you see there's one saddle right there where things are going out and other things are coming in, and then one source. So you can turn this broken, I'm sorry, not broken, but this periodic orbit, this loop, into a saddle and a source. And now this is an honest Weinstein domain instead of a Liouville domain, because in backward time, everything flows to a critical point, one of these two, and there are no broken loops. And then the third condition we said was generic. It's that locally you look like a gradient in these two. So this is the toy version in dimension 2. And the box fold here just works out on the nose. You can introduce this trapping and you're very happy. So in like the 5 minutes or so that I have remaining, I want to tell you about not toy examples. I will try not to tell you too much actually. So I'm probably going to skip some things to get to a statement of a theorem and then maybe not tell you too much about the actual computations. They get even crazier and messier. But I do want to get across the general tension that exists when you're trying to write down these manipulations. And it's a tension between trapping and holonomy. And I'll have to maybe say more about what I mean by holonomy. But the trapping is what we've talked about so far. There's just this region here in that top contact slice, which will get trapped because you just flow in backward time and you see all these things, they're running back to critical points. But this came at a cost. Like trapping is something you wanted to do, and it was very helpful in the cylinder, but it comes at a cost that these points, and these as well, but there aren't as many of them, these points which are not trapped, you're going to need to trap at some point, probably. In the cylinder case, we got lucky and we didn't have to worry about it. But what you are really worried about doing is taking a point which enters here, not trapping it, and then causing it to exit there. The reason this is bad is now you may have just totally destroyed the global dynamics outside of this box. Like the vector field is still just moving along straight everywhere. But if you're interested in the long-term backwards behavior of this flow line, and you had some knowledge of it before, you've lost that knowledge because now instead of just exiting here, and then you can say, well, eventually it'll go somewhere, is exiting somewhere far away now. So this stretching of the short blue line into a long blue line is very bad in your pursuit of understanding the global dynamics of the domain. So if you want to go around, if you can get away with just installing one fold, which is what we did in the cylinder, then you're fine. But if you ever need to install more than one fold, holonomy is your enemy. And there's just this like built-in, I don't have a way of quantifying it, but a built-in tension between being able to trap things in backward time versus messing up the dynamics via this stretching holonomy. So all of the constructions that Joe and I put into the paper are about trying to strike a balance between these two. And this is where the stabilization that I mentioned earlier makes it a comeback and is very important, because by giving ourselves that extra dimension, I said earlier that it gives you more room to tame the dynamics. Well, to be more specific, what I mean is it gives you somewhere to put the holonomy. That's still pretty vague and not very specific, but we were able to trap, and in the same dimension that you see trapping, you see stretching, you see bad holonomy. Well, by coming up with some sort of convoluted folds and convoluted plugs, we're able to trap in one dimension and then send the holonomy off into the stabilization dimension where we don't have to worry about it so much. Yeah, I'm not going to go through the actual constructions since I am out of time, but I'll try to tell you a little more about what they are. I also want to mention, because it's important to cite this result over here. We said we wanted to talk about the Stably-Weinstein case, and so there is some precedent for using the stabilization direction to tame the dynamics. In fact, the full result that we talked about earlier of making a Liouville domain Weinstein by stabilizing it, the full version of that result holds if instead of domain we say manifold. If we say Liouville manifold, this is a non-compact version, and in that setting it is true. And this was proven in 21 by these authors. But the Liouville homotopies that they produce are not compactly supported, so it does not apply in our domain case. And they use wildly different techniques. But I just wanted to emphasize there is precedent for thinking about the stabilization. So yeah, if you'll forgive me for going maybe a minute over, I will tell you the main result. So I have in here all the tools that we use to build it, but those are maybe too technical to discuss in 30 seconds. So the main application of our tools that we developed is that those torus bundle Liouville domains that we visited earlier, the thing that Mitsumatsu and Geiges constructed in dimension 4 and that Huang later generalized, these are all stably Weinstein. If you apply one stabilization, then you turn this 4-dimensional domain with index 3 handles into a 6-dimensional domain. And suddenly those wild dynamics that existed before, we have enough room to tame them, and we can make that Weinstein. So you know from the topology that you're going to need to stabilize, and what Joe and I proved is that one stabilization is enough, and now it will be Weinstein. And we did this by constructing plugs which balance the trapping and the holonomy. So I will leave you with that statement rather than running through all of the constructions on later slides, but I'm happy to talk about more details of those if you like. Thanks.
Thanks, Austin. So, any questions?
I have a question. So So this result of yours
Mhm.
is the argument that you construct like very explicit for these family of examples?
So the this isn't much of an answer, but this portion of the argument is specific to those examples. What I mean is, in the slides that remain, I tell you about the blocking apparatus, which is a very general tool, just like a box fold is a general tool, and they can be applied in any number of settings. The only setting that we've actually worked out the details of is this torus bundle Liouville domain. But then, of course, a natural question, if we were to run through what are the blocking apparatus, you could ask, well, could I take any stabilized Liouville domain and install these blocking apparatuses to get a Weinstein domain? I don't know the answer to that. There's actually a paper that cites our paper and claims that we did that. We did not do that. We showed it for this one large family. I've talked to some people who think these blocking apparatuses we built could be used on any of the known examples, but I haven't actually done it myself.
Do you think they could?
I think on McDuff's they could. I should say I don't know of any examples or any good reasons to think that they wouldn't work on any of the known examples. What is much scarier to me is the original question of what if you have a Liouville domain which does not have any handles of high index, but you don't know that it's stabilized. So if you have a 6-dimensional domain which has the homotopy type of a half-dimensional complex, but you don't know that it's a stabilization. In that case, I'm less confident that a blocking apparatus argument could do it.
So you said the McDuff's example you believe is also possible to prove to turn it into Weinstein by this blocking blocking method.
Correct.
I see.
And then there are other well-known examples of Massot, Niederkruger, Windel, which bear a lot of similarities to the Mitsumatsu Geiges examples, in that you have these like this disconnected contact boundary, and then the disconnected components are contactomorphic to one another, and then there's just sort of a weird dynamical interaction between them. And that one I have not written it down, but I do believe that one could be done. Like that's maybe the one I am most confident in without actually doing. But after building these blocking apparatus, it took a long time to build the tools. Joe and I were kind of too tired to use them in more than one example right away.
Thanks. Could you, can I ask another question? So could you say a little bit more about the third condition about the Morse being Morse near the critical point? So like, is there say more spot or like those kind of conditions or?
Oh, right. So this is actually, I was brushing it off as just being generic. And I think as far as this sort of investigation goes, that's true. And maybe I don't have to fuss with those details so much. However, I think like in the world of Weinstein domains, this is maybe an active debate is what the right definition should be. Because if you go and look at like Weinstein manifolds revisited by Eli Ashberg, when he first defines what a Weinstein structure is, he just says it's Weinstein structure. It's a Lyapunov, the Liouville vector field has a Lyapunov function, and he does not require this function to be Morse at all. But then he goes on and discusses some more about what you want the skeleton to look like, and requires that the skeleton admit a Whitney stratification, which is not true. Like you can write down vector fields where this doesn't happen. So it's strictly stronger than just, oh, there is a Lyapunov function to say that there is a Whitney stratification. But it's probably weaker than the existence of a Morse function for which you are gradient like. So there probably is this sort of intermediate level of regularity that you could get away with if you just want to do skeleton manipulations. So Morse bot is probably good enough, but Joe and I stuck to Morse because that's sort of the strictest one that gets used in the literature, and definitely in that case you could get a handle decomposition.
Thanks. Any other question?
I've got a really naive question, probably for anyone could answer this, but why does Weinstein domain care about low dimensions, and what is the issue with higher dimensions?
So it's not the dimension that creates a problem. A Weinstein domain can exist in any even dimension. It's that a Weinstein domain wants low index on the critical points and therefore on the handles. So this was like the first topological obstruction that was noted. Let's see if I can find it. So we had this statement back here that if you have a Weinstein domain, then each of those critical points of your vector field has to have low index. So that's why we all the way through were saying, oh, this thing had high index, therefore it can't be Weinstein. If you're asking why this is true, I am happy to answer that, but I don't want to answer the wrong question.
Yeah, I think I'm curious, like, why is that true? But maybe this is, yeah, maybe I can like talk about this later, because maybe this is not even within the scope of like your
No,
presentation at this point.
it's a great question. So why it's true is actually maybe something I should have addressed in the first place, because it is helpful to understanding what exactly is going on here. And if you have, so I'll give you a moral reason, not actually a computation. But if you have a Weinstein domain, you want to think of this as giving you a handle decomposition of your manifold. So maybe you have, this is in dimension 2n, so maybe these are k dimensions here and 2n minus k dimensions there. So you have some directions going in and then some directions going out. And these directions going in, that would be the stable manifold of your critical point.
Mm-hmm.
And you can do a computation. That's the computation that I'm going to skip right now, but it comes down to the condition that the Lie derivative in the direction of x of the form lambda must be lambda.
Okay.
I don't think I wrote it down in exactly that way, but something I wrote down is equivalent to this.
Mm-hmm.
This tells you that if you take omega, which is d lambda, and restrict it, so I should write it as d lambda, to the stable manifold, and the stable manifold, to be clear, is this.
Yeah.
Then you get 0 everywhere. So this is the computation that I'm skipping.
Okay.
Once you know that, we can say, therefore, the stable manifold is Lagrangian. And then it's a general fact of symplectic manifolds that Lagrangian submanifolds have dimension at most half the dimension of the manifold. This is a glib way to say it is this is like a linear algebra fact. Once you know that this is 0, it's sort of like then you have to unwind what does non-degeneracy mean for omega, and the fact is the largest dimension you can have this thing be 0 on is half.
Okay. Thank you.
Thanks.
Okay, then let's thank Austin again.